so we have all those problems, but what are the solutions that we see there? And for us, one of the solutions has been workflows. So basically force everybody to create a workflow, which we define as a chain of well-documented process steps that create or handle data for a specific problem and that are used to deliver a particular set of outputs. So by formalizing basically what you're doing in those steps, it's easier to reproduce what you have done. So of course, if you take this XKCD for a scientist, you really want to see, does it really hold true? If I do this multiple times, do I get the same result? And also, can I change things? And it's also a very big cornerstone of those FAIR principles, which are well known, I assume. If you want to make your data available, it should be fair so that people can find it, use it, interact with it, and then also reuse it. And so how this translates in our world idea is that you basically have, instead of having like all those different people running their software the way they always have done it, that they basically create modules, encapsulate in modules, describe what is the input, what is the output in an interpretable format, and then that you can combine it into a workflow that is executed on a HPC system or whatever. So basically that those modules are easily reusable and well documented. And if you take this multi-scale simulation again, the idea is then, of course, you basically have those different tools and where you just need to know the different parameters you need to adjust instead of having to know how to transfer this to the HPC system, how to actually run this on the command line and all these very intricate things which are important for getting this to run, but not necessarily for understanding the science or doing the simulation. All of this, just a short caveat. I mean, there's always the idea you can automatize a lot, but you should still be understanding what you're doing. So for example, if you take a MD simulation, you can automatize this, that you just put in a molecule and then run this simulation, and you spend a lot of compute resources, but at some point you just get garbage out. So if you put garbage in, you get garbage out. So there's still some need to understand what you're doing, and what the technique is actually doing, if it's usable for what you do. So, I mean, workflows can try to help catch those kind of issues, but it's probably impossible to catch all the things that can go wrong. So ideally, you should still know what you're doing and how much resources you're using in the end. But if you have these technology, then you can go to also very complex problems, as Tilman will kind of explain here.
Yeah, so I take up here an example shown a few slides earlier, this high throughput study, how nice it would be to be able to do this automized. It's not how nice it would be. It does work. So you see here a screenshot how such calculations are done in Python. You can download the link here and play with this example yourself. I wanted to emphasize here also to somehow indicate the opportunities. It's not only that we have with this a way of producing a lot of data, and that's way, but as I said before, in this way fill knowledge graphs and enrich our knowledge in terms of data, but because we also know where the data are coming from and how they are connected, you can then also do knowledge generation. So that's an example here. So in the first place, in this high throughput study, we look at the segregation energy. We want to know how easy is it to put my zinc atom in the grain boundary as compared to having in the rest in the matrix material and the bulk, how we call it. And we do this for different elements. So we know for every element at the end, how easy it is in iron to put this element at a specific grain boundary, or actually a variety of grain boundaries looked at here. Yeah, and then you can also ask yourself, okay, grain boundaries, there was liquid metal embrittlement, there is this kind of key cohesion of the grain boundary. So that would be another kind of descriptor. We take here the work of separation. Separation means I have the grain boundary first as a microstructure feature, and then I separate to two grains, and then this way open a crack. And so this kind of two seemingly independent kind of processes to segregate to a grain boundary and to separate two grains at the grain boundary are described with two different workflows, but we can combine the data from these workflows because we know the provenance of the data, we know the underlying concepts, and then we can also correlate this data. And so that means we can learn something about how is segregation tendency and embrittlement density somehow coupled, and there may be a coupling or not. I cannot go deep into the material science here, but just want to highlight the kind of opportunities you have if you have data not only as data, but with their underlying workflows, how you get to this data.